Today we will move into another controller, the last controller in the course, which is PID, proportional integral derivative. This is, as mentioned earlier, is a combination of PI and also PD controller. As we know that PI is used to improve steady state error, PI for steady state error, and PD for transient response. By using PID, we will be able to improve steady state error and also transient response. If we require to improve both, to have both objective, improving steady state error and also transient response, then we need to use the PID controller. It's a combination of PI and PD controller. We can, in designing PID, we have to design one by one. First PI, then PD. Or we can also design PD, then PI. Both are acceptable. In the course here, we will first design for transient response. That means we start by designing PID, then we continue with designing PI. So the sequence is PD, then PI. Here, as we already learned before, PD is more difficult to design. We need more calculation. PI is simple, just take the number, no calculation. So in this case, if you're familiar with PD, then you should be able to do PID. The transfer function for PID, GPID, is KP. KP is the gain, we call proportional gain, plus KI over S. Integral gain, we divide by S because integral, plus KDS. This is derivative. For derivative, we multiply with S. It can be rewritten if I take a common denominator S. So it will be KPS plus KI plus KDS squared. Or it can also be written if I take KD S squared plus KP over KD S plus KI over KD over S. Yeah, I just take out KD and make a common second order system S squared, second order. So we can also view GPID like this, which is PI. We start with PD, which is, we know PI is S plus Z over S. That is PI. Z is small. Then PD is just Z. I call Z Z1 and Z2. PD, we add another 0, and we multiply with again K. This is the same. Both are the same. So in PID, actually we add 2 0. See, 2 0, Z1 and Z2, and 1 pole. 1 pole at the origin. In order to obtain, in order to increase the system type. That is for PI. So PID in total 2 0 1 pole that we add into the system. This is the block diagram. in which here also is actually the same. We can get the signal here is Ki plus K2 over S plus K3S. It's just they use I2, 1, 2, 3. It's actually the same. KP, Ki over S, KPS. They normally also described in a block diagram like this. Okay, next we will continue with an example. We will do two examples today. Given a system, design a PID, mention PID here, so that the system can operate with a peak time that is 2/3. We want to reduce 2/3 from let's say 3, we want to reduce to 2. 2/3 of the uncompensated system and overshoot 20% and 0 steady state error. See, in here we want to improve transient response and also want to reduce error to be 0. Then we need PID. We need a PID control. Sometime in the question they did not mention PID. Design a controller. So based on the specification, you have to know, you have to decide which controller to be used. Okay? So let's start. Normally, for this question, root locus will be given in the exam, so you have to know how to read the root locus. I will write this here into, this is the system. S plus 8, 3, 6, 10. So if we draw root locus, it will be like this. I will just sketch. We have -3, -6, -10, repose, and the root locus will be in here, will be like this one, and will be like this. This is the root locus. Oh, sorry, it will be, oh no, it should be PID. Locus will be like this. Again, I made mistake. This should be 1, 1, 0 at -8 here. Okay. So this will go here. So that's why it will be like this. So this is the root locus. We want 20% overshoot. Overshoot 20%. We can calculate zeta. If you calculate 0.456, you can use the graph. And the angle is 62.9 degrees. That is the angle. So we make the angle 62.9 degrees. We will get, this is the closed loop pole, the original closed loop pole. If you check, if you do, it will be some about plus J 10.57. I took from the book. That is the closed loop. This is the closed loop pole. Original system. Then we have, as the standard procedure, we need to analyze the original system. Yeah, so based on the closed loop pole, we can calculate for TP, pi over omega D. This is 0.297 second. We can calculate TS, 4 over zeta omega N, 5.415, which is 0.378 second. We can also calculate error. Okay, we can here. We need to calculate K using the length L1, L2, L3, L4. We did this many times. So K here is L1, L3, L4 divided by L2, and it will be 1 to 1.5. Please, I just give the answer. You should try again to get that value. Then if we know K, we can calculate for error, which is error here is 1 over 1 plus Kp. So this is a type 0 system in which Kp is limit S to 0 GS. Then if you calculate, we get 1 to 1.5, 8, 3, 6, 10. And Kp is 5.4, and error is 0.156. This is the original system. And we have to design a PD controller based on the original system. In order to design a PD controller, as I mentioned just now, we will first design a PD controller. And later, once we finish PD, we continue with PI, and then we multiply together. Okay, what we want is TP 2/3 of the TP. This is new one, TP new. We want to reduce by 2/3. 2/3 is from 0.297, the original one. This is the original peak time. So it is 0.198 seconds. This is what we want. We want the system to operate with a new TP of 0.198 seconds. So next, we need to find the new closed loop pole. Okay, to achieve that, TP equal to pi over omega D is 0.198. Then we can get new omega D, pi over 0.198, which is 15.86. We can we can imagine like this. 15, this is the zeta line. Zeta is mentioned here, 0.456, theta 62.9. So here 62.9 degrees, zeta 0.456. If this is the one, the point here, which is 15.86, we can find this point, negative zeta omega n, by using trigonometry, okay, in which tangent 62.9 equal to 15.86 over x. This is the x value. Okay, so x here is 8.13. Therefore, this point is minus 8.13. And so therefore, the desired closed loop form is S equal to minus 8.13 plus minus J 15.86 obtained from here. So we managed to find the desired closed loop form based on desired transient response to reduce peak time. So now we want to proceed to design PD controller. Design PD controller. Okay, we design by adding 1, 0. This is the original. We have minus 3, minus 6, is it? Minus 6, minus 8, minus 10. The point that we interested is here. Minus 8.13 plus J 15.86. For PD, we will assume that we add another pole, Z, and we want to find Z. Then we need to, in order to find Z, we have to use the property. Then we have to determine all the angles. The 1, 2, 3, 4, and 5. We did a lot yesterday, in which we have theta 1 plus theta 2 plus theta 5 minus theta 3 minus theta 4 equal to 180 degrees. So please do it, finding all the angle, and what we want is theta 3. Theta 3, if you calculate, it will be 18.13 degrees. Okay, that means the location of Z is on the left of the closed loop pole. Right, we proceed to find Z. So we know this is the point minus 8.13, J 15.86, and Z is here, in which the angle is just now 18, angle is 18.13, sorry, 18. Should be 18.3, not 13. 18.3. Cannot be. 18.3 degrees. So here 18.3 degrees. You can use trigonometry, then Z is equal to 56. Please try. Therefore, GPD is S plus 56. I'm fast here because we did it yesterday. This is GPD. Okay, once we have done PD, we will proceed by designing GPI. Remember, PI is S plus Z over S. Okay, and Z must be small. There is no calculation of Z in PI. You can choose a small value, can be 0.1, can be 0.01, can also be 0.5 if you want. Okay, so everyone will choose their own Z, which is small. In this case, I just choose 0.5, just as an example. You can choose 0.1, you can choose 0.02, whatever. Therefore, we have PID, in which we multiply GPD and GPI. So we have S plus 0.5 over S, and also S plus 56. PI multiply with PD. And we have K also here. The next task is to find K. How can we find K? We can find K by also using the same technique in which we calculate the distance. So now we have to include all 4 and 0, including the controller, including the one from the controller. So we have before minus 3, minus 6, minus 8 here, minus 10. Then we have one pole on the origin due to PI. Small one here, minus 0.5. And here, another 0 at minus 56. And our interested point is here, minus 8.13, J 15.86. Then again, we need to calculate L, L1, L2, L3, 4, 5, 6, and 7. Okay, L5, 6, 7. In which K is L1, L2, oh no, sorry, not L1. K equal to L2, L4, L5, L1, L7. Divide by L1, L3, L6. Then you get the value of K, which is later substituted into GPID. Then we get the final one, GPID controller. So that is the procedure in finding PID controller. If you calculate, K here is about 4.6. It is from the book about 4.6. You may get slightly different value. And finally, 4.6 S plus 0.5, 56 over S. We can, if you want, we can still proceed, because remember GPID is we just now we did like this. Okay, we also get 4.6 over S. Then here is 4.6 S squared plus 56.05 S plus 28 over S. If we can write in this form, then we can equate KD is 4.6. Right? KP over KD, we can equate here. KP over KD is 56.5. Then we can get KP. Multiply with KD. KD 4.6. And here, finally, KI over KD is 28. We equate here and here. Then we can get for KI, 28 multiplied with KD. Okay, that is the final one. In order to design PD, we will stop until here. Any question before we proceed? Any question? This is the, if you read through the book, they give the root locus, the one without, this is the one without controller and compensated. This is with PD controller. You can see that this is the one that the point that we want. Okay, we managed to get This is the one, this is 56, this is PD. Then this is become PI because they add another one pole at the origin and 1 0 near to the origin. The type of the system will increase by 1 and the error will be 0. This is the time response. You see, this is the without control, without a controller. This one is only PD. Is good, but still we can see there is an error. But with PID, the error is improved. And we can achieve both, which is a good transient response and also error, zero steady state error. Okay, this is one example. Final exam 2018-2019. A third order system, given GS here is a third order system. Okay. A, initially the system operated at this damping ratio, this overshoot, and also omega n is given. Omega n is given. Determine the closed loop dominant pole and the gain. They want you to find closed loop pole and also the gain. Compute the settling time, peak time, and steady state error. So here is we want to analyze the original system. Analyze original system. Then using the same overshoot, design a PD controller to reduce peak time to half. We want to use PD to design to reduce the peak time by half. That is PD. Then the question continue. The controller design can be further improved by incorporating the PI controller. This is given. PI is already given here. S plus 0.02. And the value of Z is already given. By combining PD with PD design, PD controller design, by combining PD and PI, form the overall transfer function and find Kp, Ki, Kd. Show that the error is 0 and then sketch the root locus. So this is the way, this is one example 2 years ago from the final exam. The overshoot, mentioned overshoot 25.4%. And omega n is given as 6.57 radian per second. Of course, you can use the table, the graph. You can get zeta 0.4 from overshoot. And we know that the dominant pole, the closed loop pole, is S. It's always like this. Okay. In this example, root locus is not given, but the information given is sufficient to design PD and PI controllers. So from here, we can get the dominant pole minus 0.4, 5.67, minus J, omega D, omega N. N is 1 minus zeta squared, 0.4 squared. You solve, you get 2.628 plus minus j, 6.02. So that is the dominant pole. We answer question A, one of the question here, dominant pole, and we need also to find K. Finding K, we can sketch. We can use the pole given, the 0 given, minus 12, minus 3, minus 6. You can see here, there are 3 poles here, 3, 6, 12, negative. And the point that we interested is here, 2.628 is 0.2. Then we can find K by taking the length L1, L2, L3. K, L1, L2, L3. Okay. If you calculate, you get K 464.8. This is K. Then we can analyze the system, find settling time, peak time, and error. Settling time, ES 4 over zeta omega n, 4 over zeta omega n, 2.628. It is, if you check, if you calculate 1.52 second. Peak time, pi over omega d. Pi over omega d is, this is omega d, 6.02 is 0.52 second. And error. Again, here is a type 0 system, a type 0. So we use 1 over 1 plus Kp, in which Kp limit s to 0 Ts, and we will get 464.8 divided by 3, 6 squared. And error is obtained as 0.317. You get Kp, then solve error. That is the original system. We need to proceed to, according to the question, to design PD controller to reduce peak time by half. Peak time 0.52, we want to reduce by half. New peak time is 0.52 by 2, 0.26 seconds. This is what we want. Tp pi over omega d equal to 0.26. Then new omega d is pi over 0.26, which is 12.08. Therefore, we can also find another on the real axis. This is zeta line. Zeta line to achieve 0.4 damping ratio or 25% overshoot. Zeta 0.4. If you check, this should be 66.4 degrees. If this is 12.08, using trigonometry, we get this value 5.27, negative. Therefore, the desired closed loop pole is S minus 5.7 plus 100J 12.08. We need to design PD controller to achieve so that the pole is on the new root locus. Okay, design, you can proceed by design PD. As usual, same. We have 3, 6, 12, 3, 6, 12, and 1, 0 we add for Z. And this is 5.27, J 12.08. If you calculate, you will get Z. The Z using the root locus property, Z equal to 10.14. I want you to calculate. It is 10.14. Can use the one that we using the angle, find the angle of Z, then you get 10.14. That is GPD. S plus 10.14. That answer, we have done these two. Okay, B, now design PI controller. PI, we want to design GPI. We know that GPI is S plus Z over S. Z is small. But in this question, it is already given. Use Z as 0.02. Then we just use that value, S plus 0.02 over X. This is PI. So PI is simple. Just use a small value of Z. Combine PD and PI, then find KP, KI, KD. We can proceed to design PID. GPID is we multiply KP, PI and PD. PD S plus 10.14. PI 0.02 over S. And we have K in front. We need to find K again by using the distance. We have minus 3, minus 6, minus 12. Here 1, 0, 10.14, 1, 0, 1 pole at the origin, and 1, 0 at near to the origin, 0.02, negative. Okay, our point is 5.27 here, 5.27, J 12.08. Then we can calculate for K using the length L1, L2, and so on. L1, L2, So you can proceed to find all K, 3, 4, 5, 6. K is L1, L3, L4, L5, 3, 4, 5, 1, 2, 3, L6 divided by L2 and L5. You calculate K is around 158. Therefore, we can include here we know that GPID can also be written in this form, KD S squared, KP over KD S, KI over KD over S. We derived just now based on in this form. And of course, the one here can also be written in the same form. If we open the bracket, we get S squared 10.16S plus, if you calculate, becomes 0.2028 over S. Then we can equate, therefore KD is 158, KD is this, and equate both. KP over KD is this, and KI is here. We equate to get the value. KP over KD is 10.16. Therefore, KP is KP 1605. 158 multiplied with this. KI over KD is 0.2028. Therefore, KI is 52.04. That answer here, finding KP, KI, KD. We need to prove that next we need to prove that error is 0. Of course, if you calculate, error will be 0 because the system now is the type of the system is increased by 1 by adding a 0 pole on the origin. And the question want you to proceed to sketch the root locus. Okay, any question? Please, I'm sorry I did it in a fast way. I hope you have done it. If not, please redo it again. Follow the same procedure. You can complete that one by this one, prove 0 error, and sketch the new root locus and the output. This is the term here is just sketch. No need to draw the exact one. In the next lecture, we will continue with tuning of PID controller. Tuning is one of the issue in PID controller. Tuning means to find KP, KI, KD. There is, besides using root locus, there are many other ways to tune the controller. to find the Kp, Ki, Kd, known as PID gain. We will show two techniques in tuning PID controllers. In fact, there are many other techniques. Any